us explore some more questions in understanding DFA to RE conversion procedure. Here is an automaton which reads so many B's at Q0. On reading A, it goes to Q1 and accepts. It can read couple of B's here. On reading another A, it comes back to this. So we clearly see that it accepts just A, prefixed and suffixed with so many B's, and then this pattern repeats. So we clearly see that it accepts odd number of A's. Now let's find a regular expression for this. And in one of our earlier lectures, we saw that 4 different regular expressions can be constructed using the pattern. But now what we will do, we will find out through our procedure. Let's construct system of equations and solve them using Auden's theorem. So Q0 being the start state, you get epsilon plus, then look at incoming arrows, state followed by the symbol and state followed by the symbol. So for Q1 it is state followed by the symbol, and from Q0 it is A, so it is Q0 A. Fine. So what we will do, we need to simplify this to get solution to Q1, which is precisely the final state. So from this, one can write it as Q0 B plus Q1 A plus epsilon. So this can be seen as R equals RP plus Q, and the solution is, if R equals RP plus Q, then R equals Q times P star. Therefore Q0 equals, in this case Q is Q1 A plus epsilon times B star. Now let's go here. So Q1 is Q1 B plus Q0 A. Q1 equals Q1 B plus, in place of Q0 substitute this, we get Q1 A plus epsilon times B star times this. So on simplification we get Q1 B plus Q1 A times B star A plus epsilon times B star A, which is B star A. Now taking Q1 common, it is B plus AB star A plus B star A. See, always we follow state followed by the symbol. This symbol is a regular expression, so which means when you simplify, you always write state followed by the regular expression. Okay. And as far as math is concerned, you can also write Q1 on the other side, but we always write state followed by the regular expression, because that's how we build this. Otherwise there may be inconsistency when arriving at the solution. So always write state followed by the regular expression. Now Q1 equals this is like R equals RP plus Q. So from this we get that Q1 equals Q is B star A and P is B plus AB star A whole star. Now you can substitute over here to get the value of Q0, but Q1 is our final state, so which means this is precisely what we need. Now this tells you that B star followed by A is a valid string, or B star followed by A. Then one can read couple of B's, which is done using this. Then the pattern repeats: A, B star, A, B star, A, and between A, B star to A, B star, A, you want to read couple of B's, use this. And in fact, when we derived 4 different regular expressions, this was one of them. Fine. So now this tells you that a systematic procedure like this will always help us in getting regular expression for any given deterministic finite automata. So you should keep in mind that for the start state epsilon comes, and the procedure that we follow, we always write state followed by the symbol. This symbol is a regular expression, and so which means on simplification you always write state followed by the regular expression. So let's look at couple of more, and in the process we get to understand why this procedure is working fine. Intuitively you see, at each state we try identifying the sub-regular expression, and all that we build or we kind of use it when we want to solve Q1, and the solution to Q1 is precisely what we want. So the sub-expressions we get at each of the stage, and each of the stages will help us in solving Q1, which means all of this will eventually contribute in constructing regular expression for Q1. So let's look at a couple of more examples. Consider this language: set of strings over A comma B containing the pattern ABA, which means we start from Q0 and read A, read a B, then read another A, we accept. So this is the simplest possible string that one can think of. It is containing ABA, which means at the end one can read any number of A's and B's. To start with, any number of B's is allowed. After reading A, I can still read more A's. We will still ensure ABA is ensured. After this, when we read B, then so far we have seen AB, that pattern is lost, so we have to read the pattern again. Then on reading A, we go here. Now it's clearly a deterministic finite automaton. With respect to each of them, AB is defined. Now let's find RE for this using our procedure. So Q0 being the start state, it is epsilon plus incoming arrows, state followed by the symbol, state followed by the symbol, and for Q1 incoming thing are from Q0, so it is Q0 A plus Q1 A, and as far as Q2 is concerned, it gets one arrow from Q1, so it is Q1 B. Now let's look at Q3. So for Q3, one from Q2, another one from Q3 itself, that could be either A or B. So we have translated this spec into a sequence of equations and satisfying our requirements. Now we need to solve this system to get solution to Q3. That would be our desired regular expression. Fine. let's look at which one to simplify first. I see that Q1 equals Q1A plus Q, and let me take this and simplify first. So Q1 equals Q0A plus Q1A. So you can see this as R, this is RP, this part as Q. So therefore Q1 equals Q is Q0A and P is A, so we get A star. And it is clear from this mission as well, if you are at Q1, whatever you have seen at Q0 followed by A star. What is seen at Q0 we don't know until we solve for Q0. But whatever value you get at Q0, from that if you concatenate A followed by A star, that would be the partial string until Q1, or the regular expression until Q1 is precisely this. Okay, so now on one side you have Q2 equals Q and B. So for this one cannot apply Auden's theorem, but for this one can apply. So in place of Q2 let us substitute Q1, and in place of Q1 let us substitute this, so that everything will become Q0. So let's take this. So if you take this, Q0 equals epsilon plus Q0B plus Q2B. Q2 is Q1B, so we get Q1BB. So Q0 equals epsilon plus Q0B plus, in place of Q1 substitute this, so we get Q0 A star followed by BB. Now this one is Q0 equals Q0 times B plus A star BB plus epsilon. Now this is R equals RP plus Q. This implies that Q0 equals epsilon times B plus AA star BB whole star. Now you are at Q0. Can you really see this pattern? Yes. We may read any number of B's, so which is why B star comes. Or it could be A star, B, another B, to that you take a star. Because this pattern can repeat, right? A star, B, B. I keep repeating this. But after taking A star, B, you may want to read this one, B star, then use this. After reading this B star, you may still take this cycle. So A star, B, B. So that's precisely what we get over here. Correct? So now we have value for Q0, value for Q1, and which means we get value for Q2. Let's go to Q3. If we go to Q3, Q3 is Q2A, and Q2A is Q2A plus Q3 times A plus B. And what is Q2A? It is Q1B. So we get Q1BA plus Q3 times A plus B. And what is Q1? Q1 says Q0 A star, and value of Q0 is here. Q1 is Q0 A star BA plus Q3 times A plus B. And the value of Q0 is B plus AA star BB whole star followed by AA star BA plus Q3 times A plus B. Okay, so now you can see that this expression is like this one is R, this one is R, this part is P, this entire part is Q, which means if you follow the formula, what do we get? We get B plus AA star BB star AA star BA times A plus B whole star. Correct? It is Q into P star. So this is precisely what we get. Now let's look at this. It says this part. So I can simply take B from this. So B star followed by, let's assume this is not taken into account. Then it is A star B A followed by A plus B whole star. Or you may go through this cycle any number of times. A star B B so many times. In between you can also take B star using this. Finally you take A star B A followed by A plus B star. So this cycle is captured via this. Once you have decided to end the cycle and take to Q3, then take A star BA. When you are at Q3, you can read any number of A and B's. So this is precisely the regular expression corresponding to this. Now as you can see, a tricky expression like this one can obtain using this procedure in a systematic way. So when you look at this and try identifying regular expression directly, then what will happen? You might miss this cycle. So one has to pay attention to cycle of this type. Because there is an incoming arrow. So far whatever we have seen, we just had epsilon and a self loop. But somewhere down there is an arrow to input state. So that should be taken into account. Fine. One can also write a formula like this, regular expression like this, containing this. So A plus B star before this, followed by ABA, followed by A plus B star. But now, when you look at this will only correspond to a non-deterministic finite automata. And from that, one has to apply subset construction to get a deterministic DFA, a deterministic finite automata. But what we have started off here is a deterministic DFA, and this expression corresponds to a deterministic DFA. Okay, and but strings that are accepted by this and strings that are accepted by this, they are one and the same. The language represented by this regular expression, language represented by this regular expression, they are one and the same. But this is obtained from a deterministic mission, and this is corresponding to a non-deterministic mission. Okay, so one can also identify for some of them, not for all, just by looking at the expression. One can say, yes, this corresponds to a non-deterministic mission, this corresponds to a deterministic mission, but they are all equivalent, because we know for a non-deterministic mission there is an equivalent deterministic mission as well. Now we have established a procedure that tells you, given RE whether it is corresponding to non-deterministic mission or a deterministic mission, we know how to construct a finite automaton. Similarly, a given finite automaton, we know how to construct a regular expression as well. Let's explore a couple of more case studies.